Hi guys. Well, as always, here are the learning objectives. Now you'll see that this will be a very short lesson. Actually, we've already done this in class. The only difference is that you're going to get a lot of time to practice this until you master it. The theory is very brief. What's hard is to just get used to the idea of thinking in two dimensions. Once you manage that, you'll be fine. Okay, so the problem that we want to solve is this. And we'll start simple and then we'll make things more complicated. So I got a cannon. And let's imagine that this is just, okay, that's a horrible cannon. Let's imagine that this cannon is just right next to the floor, even though, it looks like there's a certain height, but, things just start here. Okay, it's a super tiny cannon. Now, I have this cannon, and I shoot a projectile, and I want to know what it's going to do. And all of you know that it does something like this, right? So, and then it falls somewhere here. So, our job is to find out where this point is and where this point is. Now, as always, at the beginning we will assume no air resistance. Actually, we will always assume no air resistance, and if they tell you that there's air resistance, all you're going to have to do is draw a sketch. No calculations. Okay, so the first thing that we need to think of is, well, we don't know how to do things in 2 dimensions, but we do know how to do things in 1 dimension, right? So we know how to analyze things that go up and down, and we know how to analyze things that go from left to right, for example, right? So let's start analyzing a thing that goes up and down. So let me just make this smaller. Okay, so here's me, and I got an apple. And because I'm a restless person, see, I'm making the green in the apple. Cool. And because I'm a restless person, I keep throwing it up and down. So it goes up, and it goes down, right? And you guys already know how to solve this problem. You know that, for example, if the initial speed is 20 meters per second, you know that the acceleration of gravity is minus 10 meters per second, and you know that the final speed, right, is the initial speed plus acceleration times time, and in this case the acceleration is the acceleration of gravity, so plus minus 10 times t, right? So for example, if I asked you, how long does it take to reach the highest point? Well, piece of cake, at the highest point the speed is 0, because it stops, otherwise it would just keep going up, right? So 0 equals 20 minus 10t, and from here we easily see that t equals 2 seconds. So it takes 2 seconds to reach the highest point. And then I could ask you, so, okay, how high did it get? Yeah, avoid the joke. Alright, so how high did this thing get? Well, we can do this in many ways. I'm just going to do the long formula way, because you're supposed to know this formula already. So we know that final position is the initial position plus the initial speed times the time. Remember that the dot means multiplied, plus 1/2 of a t squared, right? In this case, final position will be, well, this is 0, because I just arbitrarily decide that this is 0. So 0 plus the initial speed, I just told you, it's 20. So plus 20 times t, in this case we know that t is 2, so 20 times 2 plus 1/2 of a, so minus 10 times t squared, that's 4, right? So that's equal to 40 minus 20 equals 20 meters. So that's the final height. Another way to do this, well, yeah, we could say, well, start at 20, finish at 0, so the average speed is 10. 10 times 2, that's 20, and we would have gotten exactly the same result. Yeah, so this you already know, it's just accelerated motion, and you've done this over and over and over again, and you should be comfortable with this. So why am I showing you this? How is this related to accelerated motion? And it turns out that it's very, very related to accelerated motion, because I could look at this same situation from a train. So, okay, now let me show you what I mean by this. So here's me now with my apple. So here's me, here's my apple with the green thing, and now there's a train that's going this way. Yes, I know, I draw amazing trains. Okay, so here's my train going this way, and according to a guy that's on the train, well, he is still, right, according to himself, so I'm the one who's moving, and I'm moving this way. So what's the apple doing? Well, the apple's not doing this anymore, but it's doing this now, right? So the question is, does the height change? Does the maximum height change that it can reach? Well, not really. I'm just looking at this from the train, right? Does the time that it takes to reach here change? Well, not really. I mean, I'm just looking at it from a different point, but anything in the vertical direction does not change at all. And therefore, the movement in the y direction is completely unchanged by the fact that I'm looking at it from here. That is, this motion in 2D has a y component that is exactly the same it would be if I wasn't moving this way or the train wasn't moving this way. Which means that I can split the movement between two movements. One, the motion in the x direction, one, the motion in the y direction, and they completely ignore each other. They don't see each other. There's just a movement in the y direction and a movement in the x direction, and I can just treat them independently. So if I know how to solve equations for accelerated movement in y, and I know how to solve equations for movement with a constant speed, then I can solve the equations for projectile motion, right? So let's get back to our cannon. So here's our cannon throwing a certain ball, right? Well, so we have two movements then. And the only difference is that now instead of calling everything x, I'm going to call the movement in the horizontal direction is going to be y. And the movement in the horizontal direction, did I just say horizontal for vertical? Probably did. Anyway, so vertical y, horizontal x. Okay, so let's first do the x movement, which is the easiest one. Okay, well, the final x will be the initial x plus the initial speed. Now, this thing has two speeds, right? One is the x speed, one thing is the y speed. So let me just draw this as a vector. So this is a vector and has two components. This is the x component, this is the y component, right? So for the x movement, I'm only interested in the x component, which I'm going to call Vx. And you get a prize if you guess what I'm going to call the y component. Yay, Vy. Okay, so I know that this is going to be the initial x plus the initial speed times the time. And now remember that I can just consider the x movement as if this thing was not moving vertically at all, right? Now if there's no air resistance, how much is the acceleration in the x direction? Did I hear? 0, exactly, 0. So that's it. That's all I need to know for the movement in the x direction. My only trouble will be to find out how much Vx is. So for example, if I know that the initial speed of the cannonball is 40 meters per second, well, I know that this is this vector here, but maybe I don't know the x, right? But if they tell me the angle, this angle theta, then I can easily compute the x. How would you compute it? Please, please, please say multiplying by the cosine. Yes, exactly. So you would just multiply 40 times the cosine of theta, and you would get the Vx in this case, right? And how would you get the Vy? Yes, multiplying by the sine. You got it right. I'm sure you did. Okay, so now let's take a look at Vy. Well, at the position in y. Now, as I told you, we're going to call this y, Let me change the color so that things get pretty. Okay, so final y will be, well, first the initial y, right? And again, you know these equations. All we're doing is putting in different letters. So plus the initial speed for the y, which we agreed was vy times t. And remember, to calculate the vy, multiply by the sine. So let me just write it down. Vy is just v sine of theta, where theta is the initial angle of the cannon. Yeah, this is also theta. Okay, and then plus, oh, now I just realized I ran out of space, plus 1/2 of at squared, right? And then in this case, the acceleration is gravity. So I'm just going to write t squared. And that's if you count that g is negative. If you are the kind of person that says that g is positive, then you should have a minus sign here, because remember that g is in the opposite direction as vy. And there you go. These are the only two equations we need to calculate anything for this movement. I'm going to give you a couple of examples of calculations in the next slides, and then after this, you're on your own. Okay, so what I'm going to do now is I'm going to calculate the range of this movement. And I'm going to do it not with numbers, but with letters. But remember, this does not mean that you should be memorizing my formulas. What this means is that you should be understanding what I did and reproducing it whenever you need to do it. There's no need whatsoever to memorize the formula for the range. That will only confuse you further. What I need you to do is to follow my reasoning. Okay, so we have certain initial velocity v, which is this, so v, and an initial angle theta, and we want to know how far this thing is going to get. Well, the first thing that I see is that this movement is symmetric, right? This goes up until here, and this goes down until here. Now, there's many ways I can figure this stuff out. For example, you could just use energies to figure the highest point and then go from there. I will do it the old-fashioned way, just so that you see every single step, but again, feel free to get creative. Okay, so the first thing I'm going to do is to figure out how long it takes this guy to reach this point. Why? Because if I know how long it takes this guy to reach this point, then I double it, and I know how long it took this guy to reach this point. And then, if I know how long it took this guy to reach this point, since its speed in x is always the same, I know exactly how long, well, how far it went, right? So, let's get started. So, when I know that the b final y equals the initial velocity in y minus gt, right? Again, that's just your regular kinematics. Now, actually I know first that the v final y here is 0, right? Okay, so 0 equals vy, which is v times sine of theta, minus gt. And therefore t equals v sine theta over g. Alright. Now, what's the range of this movement then? Well, I know that the final position is x initial, which in this case is 0, plus vx initial, which is vx because it's always the same, times t. And vx, remember, it's v cosine of theta, and then t is twice that thing, right? So 2v sine of theta over g, and therefore the final position equals 2v squared cosine theta sine theta over g. And I guess if you were so inclined, you could use some of these fancy sine cosine identities. I think this is like a sine of 2 theta or something like that, and to make it prettier. But there's no need. All you need to know is that, it's pretty straightforward, is if you understand qualitatively how this movement works, right? Now, of course, this movement can get more complicated. For example, you could have your cannon, or whatever it is, at a certain height, right? And then here you have another height, and you want to know when this reaches this. And then things get more complicated, but actually it's always the same. You always have a certain Vx initial, a certain Vy initial, given by this, given by the angle, and you will always have enough data to set up enough equations to figure this out. Remember, in this case, you have two dimensions. You have x and you have y. And therefore, the information that they're giving you is split between x and y. Right? So, okay, I want to figure out the range. Then I need to figure out when y is going to be equal to this height. In order to do this, I need to set up an equation that will tell me, as if this was only one dimension, so if this thing goes up, it goes down, when is it going to reach this height? Then when I know this, I plug it into the x, and I see, it's going to here. Well, then it's not going to touch this. Or, it's going to be over here. Then, again, it's not going to touch this. So if it falls here, it's not going to touch this. If it falls here, then it's going to touch this. It's always the same. You have some piece of information, and in those equations that I showed you before, some stuff is missing. You set up two equations, you solve them, and you're done. Okay, now comes the last part, which is so easy that I'm almost embarrassed to explain it. Imagine there's a resistance. Okay, so if there was no resistance, the projectile would do this. What would it do if there was a resistance? Now, before I tell you, just try to figure it out yourself and, trace the trajectory on the computer or whatever. And you'll see that it's exactly the one that I trace. Okay, well, since this thing is losing energy from the start, this will do something like this, right? It will not reach the maximum point that this guy reached because it lost too much energy, first thing. And second, it will just keep going down, and of course its range will be shorter because, again, it lost too much energy. And that's it. Nothing more to explain. This keeps coming up in the diploma, and it's like they're giving the point away for free. As always, we finish with the learning objectives. Now, the learning objectives for this topic are very, very, very small, but what's hard is this part here. So yes, you know that the vertical and horizontal components are independent. You can sketch the trajectory in the absence of a resistance. You can do the same thing when there's a resistance. Whether you can do this remains to be seen. We will spend a whole week doing this, and even the practical that we're going to do on Friday is going to be about this. So I do think that by the end of this week you should be very, very comfortable doing this, and then we can just move on to bigger and better things. Until then, see you later.